please do stop me if you have questions, concerns, or anything you would like to discuss. So my goal for today is that I want to do a bit different viewpoint to study C-good and C-bad matrices, and it's surely linked to the previous lecture last week, but also that they are a bit independent in terms of interest, so that you don't feel like a lot of technicalities being dropped in. And I will try to also raise some open questions today that we try, and I came back and try this summer, and I haven't been able to do anything yet. But I mean, I think that fresh ideas and important viewpoints might help, and especially from the young audience. So I will recall very quickly what we did last time, right? And then we built up from there. Again, the homogenization problem is always of the form. This is Dirichlet problem, right? So I wrote it last time like f of u epsilon, or f epsilon if u epsilon equals to f, the right hand side in u, and you fix the boundary conditions on the boundary, Dirichlet. Okay, just that. So it's equal u equals to g here, and inside you have the sort of microscopic structure, right? And last time we have shown quantitative results of u epsilon converging to u, solving the effective equation. And so, I mean, what we have shown was that, so we proved that u epsilon minus u in L infinity is less than or equal to c times epsilon, and you solve the effective equations. In general, people would write like f bar of u equals to f in u, and u equals to g on the boundary. So this is in a sort of general setting, and f bar is also called effective operators. And in this case, so here we have f bar of u, just a linear constant coefficient operator. So a bar of ij uxi xj. And here again, I'm using Einstein summation convention. So repeated indices meaning summation over that index indices. Okay. And so that was the overall theme, right? And then we did present a way to study about the correctors and try to understand about the effective coefficients AKL, and that is being studied through the so-called the cell problem of the form that I'm highlighting on the lab panel. I'm going to rewrite it again here, so that you can see. Basically, we are looking at for fixed indices, say KL, we are trying to look at the equation, solving for the equation. Again, KL are fixed. This linear operator, right, yi, yj, y equals to AKLY. This is fixed, and I have to normalize it by certain constants so that this problem is solvable. So that's a normalized constant, right? And this happens in the torus. And it turns out that because this is a linear problem, we can look at the adjoint equations, and we can study it rather quickly. Normally for nonlinear problems, we have to do it through the vanishing discount procedure and stuff like that. But for this, is simpler. So I mean, this one can be done through the, I'm highlighting now on the left panel, we look at the adjoint equations, and we find R greater than 0 with the integral equals to 1. So we call R as the invariant measures, right? So that's the invariance measures that helps us. And then we have the formula, the very beautiful formula for A bar KL. It's just that A bar KL equals to integral on the torus of AKL with respect to the invariant measure. Okay. So that's that. Okay. And locally, again, I mean, The local picture was that you have, if you do expansions around a point x naught, this would be the function u. And locally, you would have that u epsilon 0 oscillate around u. And locally, you would have that u epsilon x behaves like ux plus epsilon square v of x over epsilon m, where m equals to d square of u at x naught. Okay, so that's the local behavior. And you see that the reason why people call this one corrector was that it's oscillatory. So you see that the gradient, the Hessian are changing like crazy, right? And you only see the macroscopic behavior. So you behave sort of nicely. So in order to capture the highly oscillatory behavior, when you take in this case, when you take the Hessian, d square of u epsilon is equal to d square of u x plus d square of v x over epsilon m, right? And this is of order O1. So it's not small anymore, right? So it capture for the highly oscillatory behavior. That's why people call this one also a corrector problem. So corrector stands for correcting the behavior of the either the Hessians or the gradient and stuff like that. Okay, and that was sort of what we did last time. And moreover, throughout the process, I mean, when we try to identify, we said that it's actually not correct to just keep those two terms, right? I mean, this is the zero order terms, is epsilon square order terms. In fact, there's also a term in the between, so it's the epsilon order term. So what that's what I'm highlighting now on the left panel here in the theorem 3. So in order to capture it correctly, we actually also need to capture the epsilon order term. And the epsilon order term is being found in a quite complicated way. And it's through the C coefficients. And the C coefficient is going to be of our main focus today. And you can see that we can forget about all the complications of computations we did last time. The C coefficient is being determined solely on A. Okay, so you can just compute CKLJ is being equals to this integral. So let me write again. This is again our main focus today. So CKLJ of A equals to the integral on the torus. You just take the coefficients of the diffusion matrix, right? VKL YI y ry dy. And let me clear it out again here. K L J are fixed, right? And then in the right on the right hand side, we actually do sum over I, right? So it's repeated in I. So just to make it clear, okay. And it turns out that I mean, I am also trying to understand this quantity more. As I said, also through this summer, it is still quite mysterious to me. And I believe that this intrinsic term has further connections to various things that I haven't understood well. And I will also show you that it has a little bit connections to the previous great work by Avellaneda and Lin later. Okay. So that's that. Why did I say that it's intrinsic? So Aij is just Aij, right? So it's just A. And there's this Ry determined solely through an elliptic problem from A, right? And then and also there's the other term, VKLYI is also determined solely through the cell problem, right? The reason why it's really complicated is that we need to solve like two elliptic problems to find like VKL and R, and then we take the integral, right? Or in the discrete case, we take the summation. So it's really highly nonlinear, and that's one of the reasons why I don't have a good understanding about it yet. Okay, so nevertheless, this theorem again was proved by Sachin Guo, Yifeng Yu, and myself. What we prove is that we shouldn't just take the sort of heuristic asymptotic expansion into account, what we need to be careful is that we should do u epsilon minus u. That's the zero order term. The first order term is quite clean like this, and then the second order term is exactly epsilon square. We have x over epsilon d square u x, right? If we take this one in L infinity, it's going to be less than c times epsilon square. Okay, and then you can just move this one to the right, and then you get the result. And that's a correct way. And of course, we can conclude here is that if h, which is a mysterious term, it's created by CKLJ, right? So h of x is a CKLJ, summation over all indices repeated, J, KL are all repeated. Okay, so this quantity is really important because if it's zero, it tells us that you know, H is zero if and only if Z is zero, right? So if it's zero, then it tells us that the epsilon order term vanishes. Then in which case we have epsilon square is the optimal rate. Otherwise, if it's not zero, then most likely we have the rate is only epsilon and it's optimal. Okay. And then we thought hard and we tried to understand more, and that's why we give this definition of C good and C bad matrices. We say that a matrix is good if C is just coefficients. If C good is everything, CKLJ is always zero for all the indices. And otherwise, it's just one of the index is bad, then we say that A is C bad. Okay. And this is a corollary, and I want to clarify it also a little bit, also according to the question that Wenjia asked last time, that you know, so the corollary is that if A is C bad, then we not always have the rate is epsilon, because the problem depending on everything in a highly nonlinear way. But numerically, most of the times we have the rate is epsilon, and I want to make it clear is that we say if A is C bad, meaning that if there's a coefficient of KLJ of A is not zero, then we can find F and G such that the optimal rate is O epsilon. Okay. And again, why do we need to be careful? Because H is the combinations of CKLJ multiplied with UXI, KXJ, KXLX, right? So if there's some magical cancellation, then H might be zero, even though the coefficients are not zero. But anyway, that shouldn't be too hard to do. The proof is just that it's already written on the lab, but basically you just cherry pick F and G. Again, I mean, and again, numerically, they're quite general. You can choose many F and G. You always have epsilon rate. In the proof, right, in the actual proof, then this is just one choice. I choose GX just to be XJ, XK, XL. Those KLJ are fixed. And F is just, again, I mean, just a artificial choice. AJ, KXL plus A bar KL, XJ plus A bar LJ, XK. So if I chose it to be like that, then you look at the when you look at the homogenized limit, right? You have minus A bar IJ UXI XJ equals to F in U. You have UX equals to G, which is XJ XK XL on the boundary. And you know, again, we designed it so that U is exactly XJ XK XL, right? And if it's exactly like that, then when you plug in H of X, right, it's equals to exactly C KLJ of A, which is not zero. Okay, and then we are done. Yeah, So there can be some something repeated, but in this case it doesn't matter, right? Um, um, if they're repeated, maybe there should be some constant here, but I want to be careful actually. S, but anyway, okay. So so far I'm just reviewing what we have done, and then I have emphasized the important points of C good and C bad matrices. And my point of today is that I want to go really deep, further beyond Walpole's theory to understand about the C good and C bad matrices, and I'll tell you some interesting problems. So are there any questions or concerns for me up to this point? Okay. Yeah, I'll recall the definition of C again once I go down to the deeper analysis. But for now, let's focus on the following theorem. That there are some specific cases in which they're very simple, but those are the specific cases in which you have the optimal rate is epsilon square. So so that leads to, you know, one of the third important question according to my thesis is that we should analyze those matrices and when do we have O epsilon square conversion rate. Okay. And the reason why this theorem is important is that in practice, those situations do occur a lot. And for those specific cases, then we have really good results. And sometimes we need to be careful, right? Because if we pick, you know, if we pick some of the cases that are so good that we kind of just say, wow, I have the rate is always epsilon square, but it's just that sometimes we are lucky. So the situations are, the first one is if U is quadratic in U, then we have the optimal rate is epsilon square. And, you know, it turns out to be quite appearing quite a lot in numerics, that sometimes you choose representative examples, then many times that U turns out to be quadratic in U. Okay. Let me see this chat. The rate's lower than epsilon. It could be the case if I don't have enough regularity, but here I have enough regularity, then no. But when I don't have enough regularity to do further the expansions, and also to you see in the proof I did last time, I differentiate like crazy, right? And manipulate things. But if I don't have enough regularity on either the diffusion matrices or F and G, then it could really be the case that the rate is lower. Yeah. Okay, so thanks a lot for the question. So the first point is obvious, right? Because if U is quadratic, that means that d square of U is constant, right? And the cube of U is 0. So even though that, you know, whatever the matrix C is, when the third derivatives of U is 0 always, and I always have that H is 0. Okay? So that's the first point. That's obvious, right? The second point, again, this is important. Please keep this in your mind. Well, later, is that if I have, for some reasons, I have a specific invariant measure, so that I have that relations, right? So recall that R solves the equations that minus aij ry yi yj equals to 0. Again, this is repeated in y and j, right? And but sometimes, you know, if we are lucky, we have that aij ry just differentiate in yi equal to 0, right? If this is the case, and obviously if we differentiate more is 0. But if we are lucky, we have this, then we automatically have that the coefficients is always good, because I have C K L J of A equals to integral in the torus Aij V K L Y I R Y dy, right? And then, you know, there's nothing specific here. We just do integration by part, right? Everything is periodic. There's no boundary. So I just do integration by parts. I kick the derivatives to the other term. So Ry, Yi, VKL, Y, dy, right? And this is equal to 0. So if this is the case, and I have, you know, I have that C, the matrix A is always C good, right? So goes away. This is very simple, but it turns out that a lot of cases hold in for this setting. And finally is the case if A is even. You know, again, this is always one of my favorite point, is that once we have certain conservations or invariants, and we often have better properties, right? That's sort of the idea of Aminotter. And this is typically the case here. If I have A is even, right? It's rare, but it could be the case that I have C is that if A is even, so AY equals to A of minus Y, right? If A is even, then everything is even, right? All the solutions to the PDEs involving A is also even. So that means that I should have RY equals to R of minus Y. And also for the ergodic problem, cell problem, VKLY equals to VKL of minus Y, right? So they inherits the even properties naturally. And in particular, VKL is even, right? But if you differentiate that, it becomes odd function, right? Is it? Yeah, I think so, because the minus sign pops out. So I have VKL of Y equals to minus VKL of YI minus Y, right? So VKLYI is odd. So as a result, you take the product, right? So AIJY, VKLYI, RY, the whole thing here is an odd function, right? It's a product of even, and odd. So it's an odd function. So when you take the integral, it's equal to 0. So we are done. So those are very specific cases in which we have good rates of convergence. And believe it or not, as I said, many times once we cherry pick or once we design good examples, they turned out to be sometimes really fall into the class that we do. I believe that it's also in my mind. I mean, human minds, we often prefer something symmetric or something beautiful, and that's sort of unintentionally we choose those. And this is exactly the corollary that I have been talking about. You know, for example, if AY equals to this AI times the identity matrix, then we have the rate is epsilon square. If it's a diagonal matrix and it's specific that in the first slot it's only depending on Y1, second slot only depending on Y2, and the end slot only depending on Yn, then I also have it happens. The third case is that again, if I choose AI of Y independent of Yi, you know, so missing one slot is also the case. And the final case is when AY equals to A of Y1 only, so it depends only on the Y1 variable. Then I also have nice things happening, right? So this is again a good demonstrations that, you know, once we assume a little bit more, once we are in a good symmetric situations or invariance in certain variables, then we have good situations. Okay? And in all of those, everything is nice. Why? You can see, you can actually yeah, you can see right away, because in all of those cases I can design the invariant measures nicely. Yeah, maybe let me write down here. So in the first case that I have I assume AY is just AY times the identity matrix, right? Then you can just design R of Y to be 1 over A of Y. Yeah, maybe I should say 1 because, no, constant. No, constant. The constant is being chosen so that, so C greater than 0 chosen so that the integral of C over AY dy equals to 1, right? So C is a normalized constant. And you can see the reason why is obvious is that you need to make like Aij, Ry, Yi, Yj equals to 0, right? And in this case, because everything is 0 except the diagonal term, so you have, as a matter of fact, and in the diagonal, everything is the same, so it's going to be n times Ay, Ry, Yi equals to 0. So obviously, it suggests that we choose Ry to be C over Ay, right? So that's why. Okay, beautiful. And so I did it carefully for the first one. The second one, maybe let me just write out the diffusion matrix. You can see is A1, Y1 here. So only depending on Y1, A2, Y2, AN, YN, 0 elsewhere. So it's nice and it has certain invariance, right? Because it doesn't depend fully on all the slots of Y. And clearly, not clearly, but I mean by thinking for a bit, you can see that Ry can be chosen as C over A1, Y1, A2, Y2, up to AN, YN. Okay, just that, and you can check that is invariance, and furthermore, it's also clear that you would have Aij, Ry, Yi, and this one is just gonna be because it's only in the diagonal, right? So you're just gonna have it's gonna be Ai Yi times Ry differentiate in Yi is gonna be 0 because it independent of other slots there. Okay, anyhow, so that's the thing, and you can go same on and same forth for other cases. It's a bit boring for you, so I'm not repeating it, but you can just check me if you feel like you want to check. It's clear that those are very simple. Okay, and one thing I want to mention is that actually those examples, again, they are natural and they do appear in applications. For example, in the last case, when I have that AY depending on only Y1, A of Y1, this is often called like layer materials, or that materials only depend on one variable, so it's called layer materials, or it has some other names, and it appears quite a lot in practice, and that's why
laminated.
Yes, sorry, yeah, laminated materials, exactly. Yeah, laminated.
So I just want to make a comment because in your notes you said we select, but actually it's really solving R. But you're just solving R magically, nicely, beautifully.
Yes. Yeah. Thank you. Exactly. Yeah. So let me actually make it clearly. We can solve for R. Explicitly. Because of course R is unique, right? Up to the normalized constants, and then thanks a lot for the comment, and the laminated material again is quite important practice. You can search, and there are a lot of papers on this, and also numerics. And the second thing is that sometimes our belief was that invariance or having certain further requirements, some again either invariance or conservations lead to better behavior, and when we are lucky enough again that we can solve and find R nicely, then we can confirm the situations, and that's sort of what we believe. And then with Xiaoqin Guo, I mean, what we believe was that if we have a lot of conservations and invariants, and then we can have a better case scenario. So this is sort of like the conjecture here. I mean, we decided to make it public because we have been stuck on that for more than a year. So because of the belief, we try numerically, is because we try for the discrete setting, for the random walks, you know, in the discrete settings, we can actually write the situations as a big matrix, and then we can find R, the invariant measures, by solving like AX equal to 0. So that sort of linear algebra problems, and then we plug in everything. It turns out to be correct, and it's also in the directions of having some invariance, should give us better property. And that leads us to this question 4. And this is where at least some people I know have tried, and I tried quite hard and I got stuck. And that's why I think it's interesting, is that so question 4 is that we believe that in this case, it is in 2D. So A1y, 0, 0, A2y, with of course they are periodic, smooth enough. So A1, A2, periodic in the torus, T2, positive, of course. And just that, you know, we require that the trace is 1, right? So this is the additional requirement. As I said, we require more. Then we believe that then the question we believe is that we should be able to prove that A is C good. And it turns out that it's quite hard. We haven't been able to prove it. Here the problem is that invariant measures are not yet very well understood, and also that it coupled with the ergodic problems. But the hope is that in 2D and with this conservation, we should have, you know, better understanding. And furthermore, these situations corresponds to a, you know, random walk in Z2. So, you know, it can be casted also as a very simple random walk problem in the periodic environments. You can go up or go down with or go left or go right. It's symmetric random walk. And can we prove this? Okay. So not just Xiaoqin and I, we did actually, I mean, mostly Xiaoqin, we did a lot of numerics and also computations on MATLAB. It all gives us this. And also later on, there's a student, PhD student at Oxford. I guess that by now he's already graduated from Oxford, student of Andre Sully and Yves Capdeaubosch. So he also did a lot of numerics. And it always confirms O epsilon square here in these situations. But we couldn't find proof. So that's why we decided to make it public, because, you know, maybe the problem is simple. But what I believe is that hidden behind is something that should be understood more. Okay. And I'll come back to the second situations I mentioned here later. Once we get to, I mean, the second situations here, B here, later when I try to connect the dot with Avellaneda and Lin. Okay. All right. So those are simple steps, I guess, for up to now, because you know, so far we haven't done a lot of sorry, I'm zooming up and down. We haven't done a lot of analysis. And what's the main goal for my lectures today is actually this theorem, and it's also the main goal of the paper with Xiaoqin Guo and Yifeng Yu, that we proved. You know, we know that there are a lot of C-good matrices, right? But I mean, how big they are, you know, in the set of all diffusion matrices, and are there C-bed matrices at all, right? Maybe there's no C-bed matrix, right? Are there at all? And then how big is the set of C-bed matrices, right? And also this follows along the lines of something in dynamics, right? In dynamical system, the question is often, is it a generic property, good or bad? Which one is generic? And it turns out that we can prove that let me just recast the theorem here, that we prove is that the set of C-bed matrices is open and dense in C2 Tn maps to the set of symmetric matrices positive definite. Okay, so it's really remarkable that after quite some time of struggling, we could really prove that it's not just somewhere there, but it's open and dense. So it's quite big. And that's actually the main piece of analysis I want to show you today. Okay, so let's do it. The first lemma that I only consider it in 2 dimensions, but this can be done in any dimensions. So this lemma is actually not needed, it's redundant in the analysis. But the reason why it's important and I want to include is here is that it shows you the idea of how we proceed. So the idea of how we proceed was that, we didn't understand very clearly, so, it's always that the problem is a linear problem, right? But as a result, in the analysis, everything becomes quite nonlinear because I have the products of a lot of things. So the always the struggles of us is that we don't understand R well. But still we understand it a bit. The real struggle is that we really don't understand the VKL well at all. Yes. Yes, there's a question. Please go ahead. Yeah, or you can type it in the chat box if you feel like you want to do it differently. Okay, yeah. Again, please stop me. Otherwise, I'm going slowly here. So that's the main struggle. At least it's really hard for me to understand them well. So so we want to prove first that, again, this proof is not needed in the theorem, but at least we want to first to prove existent, right? So we want to prove that the set of C-bed matrix is not empty even, right? Because it's not clear. Earlier we didn't have any clear examples of C-bed matrices. So the proof goes like this. We first start with some nice enough matrix, but it shouldn't be too nice, because if it's too nice and we are screwed. If the matrix is too nice and it's always C good, right? So we start with, so we first show that the set of C-bed matrices is not empty. So we first start with A naught is nice enough, but not too nice. So in 2D, my notions of being nice enough is that I'm choosing a diagonal matrix, right? It should be like this. Letting one term in the diagonal is 1. The other one shouldn't be one a constant in one of the variable, because that's going to give me a good matrix, right? So I chose it to be alpha y. Okay, and you can put conditions on alpha later, whatever. It turns out that after doing the analysis, we found out that we should put these conditions that log of alpha differentiating in y1 and y2 is not 0. Okay, so we're going to require that log of alpha in y1, y2 is not 0. You can choose alpha rather easily, right? You can just choose alpha to be like e to the cosine of y1 plus y2, for example, that it's going to satisfy that assumption. Okay. Okay. So because of choosing it this way, that it means that it's not just dependent on y1 or y2, right? I want it to be sort of convoluted related to both y1 and y2, and that's good enough because it helps us to prove the first claim that r naught of y1 is not 0, right? So r naught is not too trivial. That's the point. So the proof is by contradictions. Yeah, maybe let me move to the left panel here, because this first claim is easy to prove. So let me not just repeating it. Because of the specific structure of the diffusion matrix, right? So the invariant measure solves this nice elliptic equation. So assume by contradictions that r naught of y1 is 0, then we can plug in the PDE, right? If it's 0, then that means that r naught of y1 is 0. So it gives me that alpha r naught of y2 is 0. So that means that alpha y naught of r is just a linear function in y2, right? But since that it's periodic, so it's periodic, that means that the linear part has to go away, right? Because otherwise not periodic in y2. So that allows me to have that alpha of y r naught y equals to phi of y1 only. So it's a function only in y1. Okay. And now we plug back, we have that r naught in y1 is 0, right? That's what we assumed. And we just do computations. We have where r naught y now equals to phi of y1 over alpha y. So we just differentiate it in y1. You would have, by just using differentiation rules, I have is exactly that, right? So what it implies is that the numerator has to be 0, right? Numerator has to be 0 means that, maybe now let me just write it down here. So numerator is 0, so that means that I must have phi prime of y1 alpha y equals to phi of y1 alpha y1 of y, right? And again, just everything is positive. Alpha and phi are positive, so you can just write phi prime of y1 over phi y1 equals to alpha of y1 over alpha, right? So that allows me to conclude the log of phi prime equals to log of alpha in y1, right? And since phi depends only on y1, and that allows me to conclude here that log of alpha in y1, y2 must be 0, and this is a contradiction, right? And that again, the requirement here is that alpha has to be strongly mixed of the two variables, and that allows me to from the alpha strongly mix of the two variables, and that allows me to conclude from the first step is that the invariance measure is not too trivial, right? It's sort of strongly mixed as well. Okay, so that's the first step. Okay, so let me record here. So I'm sorry that my writings left and right, sometimes the size are not the same, so I have to zoom in and zoom out a little bit. So let me recall that R solves the invariant measures problem, which is in this case that minus R of y1 y1. Wait, did I use R or R naught? R naught, yeah. Minus alpha y R naught of y2 equals to 0. So it's a nice elliptic problem. And we have shown that, so we have R is not too simple. So it's kind of mixed, right? R naught of y1 is not 0. Okay. Right. So that's the first thing. Now, the second thing of what we know how to deal with a matrix is that we first start with a nice enough but not trivial matrix, and we can sort of play around a little bit with that. And in this case, I'm going to do a bit of perturbations. perturbations here that I'm going to multiply a not with some close to one functions. So I'm going to, the goal is to define a of y to be a naught of y multiplied with a constant. So a1 of y, functions, right? So it's going to be a1 of y here, 0, 0, alpha y, a1 of y, okay? And that's that. And what I want is that a1 of y is quite close to 1. So it's just a small perturbations of a naught, right? Okay, good. And what is a1 of y here? It's quite interesting. We design it by purpose. So let me highlight it on the left, and then I'm going to recall it on the right. So I design, I know that r naught of y1 is not 0 entirely. So I take v just to be a small constant multiplied with r naught of y1. Okay. So it's just a tiny bit of that. And then I define a1 of y to be this constant, to be explained. Okay, so let's take it like this. Let's take it for granted for it to be like this, and then I'll explain why did we choose it like that. So we start with set vy equals to a tiny constant s times r naught of y1 in y, for s is very tiny. Okay, and we set a1 of y to be 1 over 1 plus vy1 y1 plus alpha y vy2 y2. Okay. Y. Right. So that's exactly that. I'm copying it from the left to the right so that you can see it bigger here. So that's our choices. I will explain why. Okay. So you see, because v is tiny, right? And vy1 y1, vy2 y2 is tiny. So a1 of y is kind of close to 1. Okay. So that's sort of the goal. And why did we choose a1 to be like this? I mean, like the reason is that by design, if we choose it like this, then we can solve the cell problem nicely for the matrix A. Okay, so this is all by design. As I said earlier, the main difficulty was that we didn't know the invariant measures. We didn't know the cell problem. So both of those are very hard for us. So to some extent, we need to find a way to manipulate them, to play with them. And this is one way to sort of design them for our purposes. And you can see that if I define A1 to be like this, then clearly just multiply everything, you know, with the denominator, right? And I should have that A1 of y plus A1 of y vy1 y1 plus alpha y A1 of y vy2 y2 equals to 1, right? So that's that, you know. So by design, by purpose, we designed to be like this. And then clearly, you know, let's call this one A2 of y, right? Then we would have that exactly. I would have A1 of y minus A1 of y vy1 by y1 minus A2 of y vy2 y2 equals to A1 of y minus 1. So this is exactly our cell problem. So exactly our cell problem. 1-1 cell problem. But I mean, let's forget about 1-1 here, you know, right? It's exactly that, you know, given this linear operators and given A1 of y, I need to find a constants here on the right, so that it's everything is solvable. So in this case, in fact, I would have a bar 1 equals to 1, right? So that's exactly that. So again, by design, we do it in such a way that we know what is our cell problem nicely. Okay, so that's the first thing. The second thing is that, I'm sorry, I'm going a little bit, they're not parallel now. Let me try to fix it. Okay, I think I can find a way to fix it. We try to make them getting a little bit smaller. Okay. Yeah, I'm trying to make it so that you can see both of the size. Okay. Yeah. So maybe this is a bit better. Now, so the cell problem is nice, and I can get a hand onto it, right? So by doing this kind of, we design by purpose, we solving the cell problem with a1 of y, and then a bar 1 is just 1. So that's just by purpose. And furthermore, the second reason is that, so we again, remember that I have the key point is r naught of y1 is not trivial. I said vy is s times r naught of y1. And furthermore, one of the last important points is that ay is just a naught of y multiplied with a scalar function. And this is another very important properties for understanding invariant measures, is that if I take two diffusion matrix that are only different by multiplying with a scalar functions, then it turns out that invariant measures are also related in such a manner. So that's really important. Okay. Then the last point is that we can relate invariant measures R naught with R. So R naught is of A naught and R is of A. So that's a really important thing when we do this sort of like stretching. It turns out that we have R of Y is nothing but R naught of Y over just A1 of Y, which can be written explicitly as R naught of Y, 1 plus Vy1 Y1 plus alpha Y Vy2 Y2. Okay. Remarkably natural, because again, if you recall, A is just A1 of Y times A naught, right? Then naturally, R naught is differ by R in that exactly A1Y scalar multiplications. Okay. And in fact, you can see also that the reason why we have is this one is that if you take the integral of Ry, right? So integral of Ry dy equals to integral of R naught y dy plus integral of R naught, the linear operators Lyy on V, right? But this integral is 0. So everything just becomes exactly 1. Okay. L naught. So it's really beautiful. Okay. So those are the key things we try. So we try to design by purpose cell problems with its solutions, and we try to design by purpose invariant measures. And then by that we are done, because now let's take the integral. So let me zoom now onto the left panel. So once we have been able to design that, so let's just compute the coefficients. It becomes A1 times Ry times Vy1 of Y. And A1 times R is just R naught, right? And then Vy1 is S times R naught of Y1, Y1. Okay. Then integration by parts gives us that exactly this integral square of this term square. And this term is not trivial, so it's not 0. We are done. Okay. So again, it's kind of like designing by purpose. And then again, I'm going to try to make it back to my space. I'm really sorry about this inconvenience. So it's A1 Y times Ry, and this is just R naught, right? And then the other terms is that Vy1 Y1, this is exactly nothing but S times R naught of Y1 Y1, right? So everything just becomes minus S integral in Tn r naught of y1 square, and this is not less than 0. So we are done. Okay. So this is, although that this is irrelevant in the proof, but what is really important for me to show to you is that that's actually our, one of the, our idea is that we need to do certain stretching, certain perturbations, and then trying to design in certain way the cell problems, and then we combine everything together. Okay. Now maybe let me prove this lemma and then start the theorem, and then we can maybe again take a break for 5 minutes if you have questions. Okay. So this lemma is simple. So let me just brief through it. So I have A map to say CKL of J of A is continuous. And once we have this continuity, then we can show that the set of C-bat matrices is open, right? Because of continuity gonna give us openness easily. And the openness is rather straightforward because you can just, you know, like a continuity is rather straightforward because you can just use the normal continuity. And because this is a normal elliptic problem, so you have VM converging to V in C2 and RM converging to R in L2 and stuff like that. So when you take the product and you pass the limit, you have conversion nicely. So then you have CKL of J is continuous in A, and then one is continuous in A, then you have automatically this corollary is that the set of C-bat matrices is open, because you know. So let me just recall this, and then we are done. So if CKL, so the set of C-bat matrices is nothing but the union over all KJL of CKLJ inverse of R takes away 0, right? Because one is not 0, then it's C-bat, and so it's just union of the inverse of a bunch of open sets. And because the map is open, is continuous, so it's open. So obviously it's open, right? So so in order to prove the result, what is needed to be done is that we only need to prove that the set of C-bat matrices is dense. This is really important, but you know, I have shown you kind of the key ideas already. We're gonna do it, but let's pause for 5 minutes in case you have questions or concerns, or we can just relax for 5 minutes. Okay. Yeah. So, and I'm sorry about my writing today. They are not parallel, and I'm, you know, on one side I wrote it in a too big font, and the other side is too small. So it's, yeah. So please.
Please ask questions. Very beautiful design, I have to say, because it's intertwined in all of the places. It's not like you start from the beginning and it will work. So it's you really get it by I don't know how did you get it?
Yeah. So I mean, good point. Yeah. So I mean, honestly, what we have done is that. So first, when we saw a lot of results saying that the optimal rate is always epsilon square, we were scared because we couldn't do it. I was like, maybe every matrix is C good, right? So, you know, and then, so the problem is also because of human minds. Every matrix we got, we try, is always C good. And it's really hard to design a C-bat matrix. It turns out that we could have it now, but only later in the paper with Timo Sprackler. I will give you the example. It's quite convoluted. So the honest idea that we started with is really that, you know, It's really that let me go back here. So so this is a corollary telling us that if we choose any examples related to this thing, then we always have that the matrix is too nice. So therefore we need to find a matrix in such a way that is highly intertwined between the variables, and that's why we first started with this example. Alpha y, and alpha y has to be really twisted. But this is not enough. So the first thing was that we tried to mess around with this example, trying to understand about the invariant measures, and we understand it a little bit that R naught is just not trivial, and that was what we can do. And then we really don't understand about VKL at all. It's really that. So what we really needed to do after some point was that this is perturbation idea. How did we come up with that? Was through the inversion, right? So it's like we look at the cell problem first, and then yeah, maybe I can say it a little bit in the ad hoc way. Let me go all the way down here so that I'm not messing around with my notation. So we first start with A naught of y is and I honestly believe that there can be better proof and more constructive ideas understanding this thing deeply, and we only have that R naught of y1 is not 0. And then we were thinking in an ad hoc way of surely, I mean, this is a natural thing to do, A naught of y with A naught is nearly 1. This is natural, just perturbations. But we really don't know what is the solution to the ergodic problem. So so what we did was that we tried to write out this ergodic problem in our way, right? Write like this. So plus A2 of y, y2 equals to A1 of y or whatever, plus A1 bar, something like that. And then and then we do it in the ad hoc or reverse way, because from here, like we can just write out A1 of y, right? Because this is A1 of y, Vy1 y1 plus A1 of y, alpha y, Vy2 equals to yeah, plus A1 of y equals to A1 bar. And then so it suggests us that we can try to start with A1 of y equals to A1 bar over Vy1 y1